All right, guys, so we are going to continue looking at buffers. So remember we said any solution that contains something that can absorb hydrogen ions can act as a base. And if you have something that can absorb hydroxide ions, that can act as an acid. And if it has both, it can act as a buffer. So remember, buffers have something that can react with hydrogen and something that reacts with hydroxide to neutralize any additional acid or base. Let's refresh and look at what type of things can be considered a buffer. So remember, you have to look and see, does it have something that can absorb hydrogen and hydroxide in the solution? So our first example, we have potassium nitrate and nitric acid. So you're looking to see if it can absorb both. So potassium nitrite, or nitrate, excuse me, can produce KOH and HNO3. Both of those are a strong base and strong acid, so that cannot absorb either because it will reionize. Looking at the nitric acid, it can react with hydroxide to make water, but then it also makes nitric acid. So it can react with hydroxide, but not hydrogen. So that is not a buffer. Let's look at the next one. We have sodium nitrite and nitrous acid. For sodium nitrite, it can make sodium hydroxide and nitrous acid. The sodium hydroxide would reionize because it's a strong base, but it could make nitrous acid. So that can be considered a base, whereas the nitrous acid is a weak acid. So remember, it can react to make water with hydroxide, leaving behind the nitrous ion. So this has a weak acid and its conjugate base, so that can act as a buffer. Looking at the next one, we have acetic acid and potassium hydroxide. Acetic acid can react with hydroxide and the acetate ion can produce acetic acid, which is a weak acid, so that's okay. Potassium hydroxide would produce potassium hydroxide and water when reacted. So here's where the acetic acid by itself, we do have a substance that can react with hydrogen from our potassium hydroxide, and the acetic acid can react with the hydroxide. Excuse me. So that because we have the weak acid and strong base, can react with both. Looking at our next one, we have sodium carbonate and sodium phosphate. This would produce sodium hydroxide and carbonic acid, and sodium hydroxide and phosphoric acid. We have a substance that can react with hydrogen in both of these, but we do not have anything that will react with the hydroxide because it would produce a strong base in either way. So that cannot act as a buffer. Looking at our next one, this is where we have one substance and we want to see if it can react with both the acid and base. The ammonium would lose a hydrogen to produce ammonia. That hydrogen would go on to the nitrite to make nitrous acid. which is a weak acid. So it produces a weak base and a weak acid. So that is one of those salts that does not have a spectator and can react with both the hydrogen hydroxide. For the last one, sodium would make sodium hydroxide, which would cancel because it would reionize. However, this dihydrogen phosphate could turn into H3PO4 or HPO4 negative 2. So that's one of those amphoteric ions that can act as both an acid and a base. So because that ion is present, that could also act as a buffer. All right, so let us look at buffer calculations. This is going to utilize ICE tables again, and we're going to look at how much of a substance can be absorbed and what the new pH would be. Right. So here we have a buffer that's made by adding 0.3 moles of acetic acid and 0.3 moles of sodium acetate to enough water to make 2 liters of solution. So, and we're going to address 3 different types of problems that you can do. First, we want to know what is the pH of the buffer solution itself. Then we want to know what is the pH of the solution after 0.02 moles of sodium hydroxide or base is added. And then we also want to compare how this is different than if we had the pH from 0.02 moles of sodium hydroxide simply added to 1 liter of water, of pure water, instead of a buffer solution. That way you can see how a buffer solution truly affects the base. So looking at what is the pH of the buffer solution. So we have a weak acid with acetic acid, and we have its conjugate base with that acetate ion from sodium acetate. So since we have both our weak acid and its conjugate base, we can use the Henderson-Hasselbalch equation to find pH. So remember, its pH is the pKa of the acid plus the log of the base amount over the acid amount. And remember, you can use molarity for the base and the acid, or you can use moles. So here we can use moles, and we have that the negative log of the Ka for acetic acid is 1.8 times 10 to the -5, plus the log of the base over the acid. And here we get that the pH is going to be equal to 4.74, and that is of the buffer by itself. To address the second problem, it wants us to calculate the pH after 0.02 moles of sodium hydroxide is added. So remember that this hydroxide is going to be absorbed by the acid. So we have to write that the acid reacts with the hydroxide. Oops. And remember, we already have some of the acetate ion at the beginning. We're reacting it with hydroxide. The overall goal is to neutralize the hydroxide. So we're wanting to subtract the hydroxide. So that subtracts on our reactant side, adds on our product side. And it is moles canceling out moles. So you don't have to worry about molarity with these, but moles canceling out moles. That gives us our new value for our amount of acid and our amount of base that are left. Once we have both of those, we have our acid amount and our base amount, we can plug back, into that Henderson-Hasselbalch equation. So that would give us a new pH of 4.80. So notice that the pH did increase because we added a base, but it only increased by like 0.06. So it did not increase by a lot. All right, so let's look at what happens if we were to add that same amount to pure water instead of the buffer. So if we added 0.02 moles of the same volume of pure water, the 2 liters of pure water, remember the concentration of hydroxide is equal to the concentration of sodium hydroxide, which is moles over liters. So 0.02 moles divided by 2 liters is a concentration of 0.01 molar, which with hydroxide ion concentration, we can find the pOH, which would be equal to 2. The pH would then be equal to 12. That is a lot higher and much more basic than the 4.80 whenever that same amount is added to a buffer solution. All right, let's look at another problem. Here we have a buffer that's made by dissolving 14 grams of sodium nitrite in 50 milliliters of a 0.050 molar nitrous acid. First thing it wants to know is what is the pH of the buffer solution? And it wants us to write a chemical reaction that would occur when a small amount of hydrochloric acid is added to the buffer solution. So to find the pH, we first need our molarities or moles for both sodium hydroxide and, or excuse me, sodium nitrite and nitrous acid. Because if we have the amount for both, we can plug into Henderson-Hasselbalch. So we can convert grams into moles and molarity and volume into moles, plug into Henderson-Hasselbalch, and get that this buffer would have a pH equal to 3.61. And that leads us to the second question. It want to know what happens if we add acid to it. What is the reaction that would occur? So remember, the acid is going to react with the conjugate base, which is the nitrite ion. Oops, excuse me. So the acid, which would be just hydrogen ion, or more commonly the H3O plus, would react with the nitrite ion, producing water. So remember, all buffer solutions produce water and nitrous acid. All right, so let's look at another buffer problem. Here we have 500 milliliters of a buffer solution that has 0.5 molar ammonia and 1.8 molar ammonium chloride. First wants us to calculate the pH of the buffer solution, then calculate the pH after 8 grams of base are added, and then it wants us to calculate the pH after a 10-fold dilution of the original buffer. So this looks at what happens if a buffer is diluted. So first, calculate pH of the solution. Remember, we can do this using Henderson-Hasselbalch with either molarity or moles. Here we do have molarity for both the acid and the base. And we need Ka of the acid, which is the ammonia, the NH4. You cannot substitute Kb for Ka using the same Henderson-Hasselbalch equation. So that would give us a buffer solution with a pH equal to 8.70. Whenever we are looking at finding the pH after 8 grams of sodium hydroxide are added to the solution, remember in our ice table, we have to compare moles to moles whenever we are trying to cancel them out. So we need to change the 8 grams of sodium hydroxide into moles. So divide by molar mass, which is roughly 40. So that means that we have 0.2 moles of hydroxide from the sodium hydroxide. So in our ice table, we have to write out our equation. So the hydroxide is going to combine with the ammonia to produce ammonium and water. We need to plug in moles for both ammonia and ammonium. So remember, it's molarity is moles over liters. So we can multiply by liters. So multiply by the 0.05 liters to get moles for both. So that means that ammonia, we have 0.9 moles. Ammonium, we have 0.25 moles. And we said there's 0.2 moles of hydroxide. Remember, our goal is to neutralize and cancel out the hydroxide. So we would have to subtract our hydroxide. So subtract from our reactant side, add to our product side to get our new amounts of acid and base. And once we have the new amounts, we can plug back into Henderson-Hasselbalch to find the new pH. So notice that because we added base, the pH did increase. However, it did not increase by that much. All right. So looking at what happens whenever we dilute a buffer. This we don't actually have to do math for. We're going to talk about it more conceptually. But if we dilute a buffer, all we're doing is changing the overall volume, which would change the molarity for both parts of the buffer equally. So the ratio within the buffer itself would stay the same. So when we plugged in that new ratio into Henderson-Hasselbalch, we would actually end up with the same pH. So diluting a buffer does not change the pH at all. So let's look at how effective a buffer is. A good buffer should be able to neutralize moderate amounts of added acid or base. So we want something that is not a super low concentration. So we wouldn't want it to be like 0.001 molar for the different parts of our buffer, because that's not going to be able to neutralize a lot of anything. The effectiveness of a buffer depends on two conditions. It depends on the relative amounts of acid and base, so how much of it you have initially. The more acid and base you have, the more it will be able to neutralize. And it also depends on the absolute concentrations of acid and base. Generally, the higher the concentration of the parts of the buffer, the more you're able to neutralize. And a buffer is going to be most effective when the ratio to base and acid in the buffer are equal to 1. So when they have identical molarities, it's going to be a more effective buffer because it can neutralize the same amount of acid and base. And a buffer is considered effective if the base to acid ratio is between 1/10 and 10:1. So even if we had like a 0.1 molar and then a 1 molar part of a buffer, that is still within ratio. But if they're too far apart in ratio, it's not going to be a very effective buffer. So here you can see a concentrated buffer that has a lot of ions in there and a dilute buffer. They're both going to be able to neutralize acid or base, but a concentrated buffer can neutralize more added acid or base than a dilute buffer. So the higher the concentration, the more they're going to be able to dilute or dissolve. All right, so here, if we consider the following two solutions, we have a buffer that is, 0.1 molar dihydrogen phosphate, and then a buffer that is 0.2 molar hydrogen phosphate. So that is a 1:2 ratio between those. And then solution B is a buffer of the same substance, but it's a 0.15 molar dihydrogen phosphate and a 0.3 molar hydrogen phosphate. Yet again, it is a 1:2 ratio. So looking at what is true about the pH of these solutions, excuse me, let it open up my new page. So they are the same ratio. Therefore, they should have the same pH. So if they are the same ratio, they will have the same pH. Looking at which solution will be able to neutralize the addition of 0.11 molar hydroxide. So hydroxide is going to have to react with hydrogen. So you're looking at which one can give up an additional hydrogen that would be able to neutralize 0.11 molar. Solution A only has 0.10 molar dihydrogen phosphate, so that cannot fully neutralize the 0.11 molar hydroxide. So solution B is the only one that can neutralize this. Whereas if we look at which solution can neutralize 0.11 molar hydronium ion, that is going to combine with the hydrogen phosphate. Both of them are above 0.11 molar, so both solutions could neutralize that acid. And looking at what's true about the buffer capacity of these, well, since the molarities in solution B are higher, solution B is going to be able to neutralize more because it has a higher molarity. So looking at how to prepare a buffer, because you're going to do this as part of your lab this week. Remember we said a buffer is considered effective when the base to acid ratio is between 1/10 and 10. And the effective range of a buffer is the pKa of the buffer plus or minus 1. So our pKa of the buffer, we want to be within 1 of our target pH. And what most determines the pH range of a buffer is the pKa of the weak acid. So the pH can range up 1 or down 1 from the pKa of the weak acid that is in the buffer. So we would want to choose the appropriate acid that has a pKa almost equal to our desired pH or our target pH. And we can use the ratio of base to acid to adjust. So if we want a pH exactly equal to 5, we can pick a weak acid that's pKa is close to 5, and then either include more base or more acid to alter that pH overall. So let's look at how this could come up. So here it wants to know which acid and its sodium salt would you choose to make a solution buffered at a pH of 4.25. And for your choice, it says calculate the ratio of the base to the acid required to attain the desired pH. So we would want to pick the acid that is closest to the 4.25 when we find pKa. So here we have 4 acids and their pKa's. The one that is within 1 or closest to our pH of 4.25. It's kind of between nitrous acid and formic acid, but the 4.25, it needs to go up 1 or down 1. So the one that's closest to 4.25 is formic acid. So we would want to make a buffer with that formic acid. And to figure out that ratio of base to acid to attain the desired pH. So we said we're going to use formic acid, which has the pKa of 3.74. We're going to plug that into Henderson-Hasselbalch, but we don't know the acid-base ratio. We know that we want a pH of 4.25. Our pKa of formic acid is 3.74 plus the log of the base to acid ratio. So you can kind of replace that base to acid ratio with X. So we would subtract the 3.74 on both sides. And then to get rid of log, we need to do the anti-log, which is that 10 raised to the power. And that tells us that our base to acid ratio needs to be 3.24. So we can do the ratio base to acid. We can do 3.24 milliliters of base for every 1 milliliter of acid. And that is what we would use to make the overall buffer solution.